Now I want to talk about RLC circuit. RLC AC circuit, an alternating circuit that is connected as a supply to a series resistant inductor and capacitor circuit. So we have a resistant here, we have an inductance of an inductor, and we have capacitor of a capacitance. Now we know that the resistor, if you don't know, is measured in ohms. The inductor is measured in what? Henry, while the capacitor is measured in what? Farad. Now each of them what provides a resistance. This one we call them reactants. Each of them what produce what they call a reactance for across the resistance, capacitance and inductance. But this one, which is resistor, produce a resistance, which we are going to be looking at. Another interesting thing is that from the previous classes that we had concerning a purely inductive circuit and purely capacitive circuit, we make us understand that what XL, which is inductive reactance, is equal to 2 pi FL, where F is what? Frequency, and L is what? Inductance of an inductor. Now, where XL is what? Measured in ohms. This is what we call inductive reactance. Inductive reactance. Now we have one called XC, which we have talked about also in our previous classes, which is what? 1 over 2 pi FC. Where C is what? The capacitance of the capacitor is constant, just like this one is also constant. What changes is reactance changes and frequency of the word AC can change. That's why when you plot the graph of frequency against inductive reactance, what you are going to have is a straight line. Then when you plot a graph of capacitive reactance, this capacitive reactance, they are measured in what? In ohms. Reactance. What we are going to have is what? Is inverse graph. A graph that look like, maybe this one now look like this, then this one will look like this. Whether if you plot the graph of what? XL against frequency. Now, but the voltage, don't forget they are connected in series, because I said what? Resistance, inductance, and capacitor in series across a supply known as the AC supply, supplying them with a root mean square current, having a root mean square voltage with a frequency. Now, when it supplies the current in the component in series, we observe that the same current will flow through them because they are connected in series. And don't forget that they will have different potential difference. Potential difference across the resistor will be different from potential difference across the inductor, and potential difference across the capacitor will also be different because they are connected in series from our basic and fundamental knowledge. Now we know that VR, according to Ohm's law, equal to IR. That is voltage across what? Voltage across the what? The resistor. And don't forget, resistor is the one that dissipates power. It causes power loss in an AC circuit. They can ask you, which of these following? This one does not absorb power. This one does not absorb power. Don't forget that this particular resistor is the one that provides a power factor of 1. Why? Because the current and voltage are in phase. But in this case now, the current and voltage are not in phase in an inductive circuit. They are not also in phase in capacitive circuit. So that is, now don't forget, the power dissipated here is assumed to be 0, and here also is what? 0. Why here is a power loss. So what really causes power loss in an AC circuit? They can ask you, which of the following component causes power loss in an AC circuit is what? Is a resistor. Now, another thing again, that voltage across the what? Inductor is equal to what? ISL. Now, if you notice, I begin to put I because the I is the same for the three component. IRMS, let me put it that way. IRMS. So what about the voltage across the what? The capacitor. It's IRMS times what? XL, SC. So these are the voltage across the what? Each component. This voltage across the what? The inductor. Then this voltage across the what? The capacitor. Now, having known the three voltage or the three voltages across each of these components, now let us now go into, for us to comprehend better or to understand what you call it, RLC circuit better. Don't forget, you cannot calculate. This voltage is never equal. The VRMS is never equal to what? The sum of VR plus what? VL plus VC, because that the voltage, this one, the current is lagging while the current is leading. So in this case, now we cannot say they are equal like this. In that case, let us draw a vector diagram in order to analyze the relationship between the voltage across the AC, which is square voltage across the resistor, inductor, and the capacitor. And let's make a sketch of this kind. Okay, see this guy now. Look at the vector diagram. This is VC, VL, and this is VR. Now don't forget that capacitors does not allow AC current to pass through them. That's why we use them for filtration. Sorry for that. We use them for filtration, to filter, to smoothing when you convert AC to DC. This will allow current to pass through them. And they are, don't forget, inductors are used to reduce what? Current variability in an AC circuit. I've talked about it in my previous video. Go and check it. It's one of the important questions you can ask. Now, if we have a leading current is leading at a 4 year, that means you have negative what? Phase angle, which is also means that what? The phase angle is also leading, current leading. Now, if you assume, let's assume. Now, don't forget that the voltage across the inductor from this vector diagram and voltage across the capacitor are what? 180 out of phase. Don't forget, I told you that the voltage across what? Capacitor, VC, and voltage across the inductor, they are what? 180 out of phase. You can see there. Angle on the straight line is what? Well, the phase difference between capacitive voltage and inductive voltage is dash. You can assume it is 180. Now, there is a voltage of the circuit, VRMS here, which is the resultant on the hypotenuse side. So let me put it that way. Now, this is what? The voltage across the what? This one. Across the what? The AC. Now, sometimes they don't give you the voltage, the root square voltage. They can give you an instantaneous voltage like this. What you are going to do is that, don't forget that VRMS can be calculated by this peak voltage. You can use the peak voltage divided by root 2. You get your what? VRMS straight. Then if they don't give you frequency, you can compare this one with what? Anything that you have here, compare with what? Your standard equation. That means this equation. Compare whatever you are giving to this equation and then solve for your frequency. So you can solve frequency from this by comparing. It's just like wave now. The way you solve wave, you can just do comparison like that. Now, this is what we call the phase angle, which is to get this opposite side of it, we assume that the VL is greater than VC, meaning that what? Voltage leads what? Current here. We assume that the voltage leads current here. Voltage is bigger than VL is bigger than VC. So the net voltage here will now be VL minus VC. That's what we're going to be having in the opposite side to this. This is VR. VR is not affected by frequency, don't forget. Now, for us to now use Pythagoras, if you use Pythagoras theorem, using what? Pythagoras theorem. If you use Pythagoras theorem, using what? Pythagoras, we have VR square equal to what? VRMS square equal to VR square plus what? VL minus VC all square. Using Pythagoras theorem. So we will have what? VRMS is equal to square root of what? VR square plus VL minus VC all what square. Now, once you do that, what is happening now? It means that we have gotten the voltage. This one can also be taken as a voltmeter reading. Voltmeter reading of the AC. Of the AC supply. So they can ask you to find that. Now, another thing is because if you check now, the phase angle here is we want to calculate the phase angle. You can use tan phi. Tan phi is equal to what? Is equal to what? VL minus VC over what? VR. Now, if you use your formula that I gave you here, these three formulas, don't forget the I are the same. If you put them there inside that formula, just substitute them, input them into this formula, you end up having what? XL minus what? XC all divided by what? R. That's what I want to ask. Now, to find phase angle, you are going to have phi equals what? If phase angle tan inverse of what? XL minus XC over R. This is how to find the phase angle, this angle. Now, anytime the word VL is greater than VC, it means that the phase angle is lagging. Phase angle is what? Is lagging. Lagging phase angle, then current lagging to current lagging, and what? The phase angle is positive. Is positive angle. Don't forget that we are going to have a positive value here because VL is greater than VC. Current is lagging, but voltage is leading. Anytime VL is greater than VC, it means that voltage is leading, while current is lagging, and phase angle is also lagging. That's what we are going to assume. Now, another thing again you have to understand there is that during this process of what? Of vector diagram we have drawn on the board. Don't forget, I told you voltage across the inductor equal to voltage across the capacitor, and voltage across the capacitor are 180 degree or pi out of phase. Now, but the current, the voltage lead the current by what? By pi over 2. Voltage leads what? Current by what? By pi over 2 or 90 degree in this particular vector diagram, because voltage VL is greater than VC. Now, in this case, let's go back to this one. Let us substitute. Don't forget that there's something I need to tell you. Your VRMS is equal to what? IRMS times Z. There's what we call Z. The Z is the impedance. I want to introduce it in now. Now, Z is impedance. Let us introduce it in. So we are going to have what? Okay, let me leave it first. Let me leave it. We are going to have, okay, VRMS is equals to what? Let me introduce what? This one will have what? IRMS times R all what square plus what? IRMS times SL minus IRMS times SC all square root of everything. Now, if you work this thing out, you are going to see that this one can also give us IRMS square R square plus what? This one can come out as IRMS into bracket what? XL minus SC all square. This one square like this. It can still come out like that because it's common. You can factorize, and when you factorize IRMS out, don't forget that if you have something like this, for example, IRMS into bracket XL minus XC. Do you know it's the same thing as this? The same thing as this. So if you now square both sides, if you square it according to indices, if both of them have square, that means covered by a bracket and they are square. Square of this one we make this one square. Then square of this one we square the bracket. So what is common on both sides again? We would have I and square root of everything. IRMS square. Square root of what? That means all bracket R square plus what? XL minus SC all square. Square root of everything equal to what? I RMS times Z. I told you that what? Z is impedance. What VRMS, which is voltage across the supply, is equal to what? The root mean square current that will flow through, the current that will flow through here. You say current that will flow through this place. You say current that will flow through this place. So it will now be what? If you factorize the square root of IRMS square will be what? IRMS, which is square current, will come out from the bracket. R square plus into bracket what? XL minus XC all square. So they can cancel out. So Z, this one will cancel out this. So Z is equal to what? Impedance will now be equal to what? Square root of what? R square plus what? XL minus XC all square. So this is a formula for what? Impedance now. That is formula for impedance. Don't forget this is formula for phase angle. Now, how do you get it? You use what? Don't forget that tan theta equal to what? Opposite over what? Adjacent. Because some of you will ask questions, say, Mr. Holiday, how do you get this formula? Tan theta, tan phi is equal to opposite over adjacent. Which one is opposite? The side facing the angle is the opposite. So this side is the opposite. Then the sitting length is the adjacent. The longest distance is the hypotenuse. So this one is what? Opposite over what? Adjacent. But if you put what? IR, IXL, and ISC over IR, you notice that the I will cancel out at both the numerator and the denominator, and thereby reduce the formula to something of this nature that you are seeing on the board. It's as simple as that. It's not difficult. Don't panic. Very easy, and it should be taken serious. So this one also is what? If you have your red pen, quickly identify that quickly. Very important. These are the points. Those three formulas for voltage across the inductor, capacitor, and what? Resistor. So those ones are taken. Also take the formula, this one that is circle. Please don't play with it. It's as important as any other thing. So please take note of that. These formulas. All these ones I was star. They are very important. But I just mentioned Z. What I do, Z is measured in ohms. And don't forget, the unit will be ohms. So and what is Z? Z is impedance. What is impedance? Impedance is the what? Impedance Z is the what? The overall opposition to the flow of what? Of current in an what? Alternating circuit, in an AC circuit. Is what? Is the overall opposition to the flow of current in an AC what? Circuit. That's what we call impedance. It is measured in ohms, and it has the formula given to you on the board. We have given the formula on the board there. Now, another thing again you need to know is that how do we calculate current? Current that is flowing through the circuit. Don't forget, IRMS is the current flowing in the circuit from the diagram that we have. So if IRMS, how do you find IRMS? From this formula now, to find IRMS is what? Divide both sides by what? VRMS over Z. And this is another important formula you should not play with. Z. So what is our VRMS they will give us? They don't give us, you can solve it. What is Z? Z is square root of what? R square plus what? XL minus XC. I just mentioned XL minus XC. Don't forget that there's what we call the net reactance. The net reactance. The net reactance is what? XL minus XC. That's what we call the net reactance. That is what we call the net reactance. So XL minus XC is what we call the net what? Reactance. So now, this is what? Current in the circuit. The current that will flow through. Don't forget, this current is a current that is flowing through the resistor, the inductor, and the capacitor. Now, in the case where VL, if they say VL is lesser than VC, in the case of VL lesser than VC, in the case of VL lesser than VC, what will happen is that it will now make the current what? Or we can say VC greater than VL. It means that current will be what? Current is what? Is leading. Current is leading. Those are leading current. Current leading. Now, if current is leading, it means phase angle leading. We have what they call leading phase angle. Leading phase angle here. Also, we say leading by current is leading. We can say current what? Lead what? Current leads voltage by what? Leads voltage by pi over 2. Leads voltage by pi over 2. And that is what? The statement you can use. And in that case, the phase angle will be what? The phase angle will be what? Will be negative. Negative phase angle. It will fall in this region. Fall below. That means if I'm to draw this, I will draw it here now. It will now come like this. This is what? The diagram, which is VL minus VC will now be giving us a negative value. Although when you square it, VL minus VC will give negative, but when you square it, it tends to not to have any effect. Because square of this one now, for example, if I say 5 volt minus 4 volt, give us what? Or 4 volt minus 5 will give us minus 1, abi? Okay, square minus 1 and minus 1 all square. It's 1 now. Or 2 minus 5, we are going to have minus 3. Minus 3 all square will give us 9. So that should not be a problem or should not be worried about at all. So that is just that. That one is clear now. Now there is something I'm emphasizing on the vector diagram, which I did that of tan. But let me do that of what we call cos. Let me do that of cos. I've talked about when VL is less than VC. I've talked about when VL is greater than what VC. Now, but there's something I need to talk about, which is what the power factor. Now, there is what we call cos phi. Cos phi is power factor, which is adjacent, which is VR divided by adjacent adjacent over what? Hypotenuse, which is what? VR over VRMS. That is what we call what? Power factor. This is what we call PF. Power factor. We know the power factor of most DC circuit or DC appliances is what? For example, the power factor of electric bulb is what? Of a DC circuit 1. Don't forget, but for an AC circuit it's not 1. The power factor of a DC circuit is 1, but power factor of an AC circuit not 1. If you ask what is the power factor of an electric bulb is what? Is 1. So and so forth and so on. Now, power factor here now is what? When you use what? IR, which is adjacent over hypotenuse, which is IZ. What do we have? This all cancels this one. So what we're going to have is what? R over Z. So this is what? The formula for what? For power factor. PF, P dot F. Anytime you see P dot F, it means power factor. And don't forget, power factor for purely resistive circuit is 1. But it is never 1 for purely inductive circuit and purely what? Capacitive circuit. Power factor for what? For resistive circuit is 1, but it's never 1 for what? For inductive and capacitive circuit. Don't forget that during resistive circuit, current and voltage are in phase. Then the phase angle is 0. If two things are in phase, their phase angle is 0 or phase difference is 0. Cos 0 is not 1. Yes, now cos 0 is 1. And so take note of that. But if you say the other ones now, they are leading phase difference, phase angle difference is 90. Cos 90 is 0. In fact, that is the reason why power, because in power, we are going to talk about power. Power factor multiplied by what we call power rating, or what we call apparent power. Apparent power is more or less like current times voltage. Root mean square current times root mean square voltage. If you go and multiply apparent power, root mean square current times root mean square voltage times power factor, will give us normal power loss. But when power factor is 0, it means that the power absorbed will now be what? So what really causing power absorbed in the inductive and capacitive circuit to be 0 is because of what? Their current and voltage are not in phase. That is just reality. Now let's go ahead to what? To explain something here. So we will get better when we want to look at question. Now let's see what this one is. Okay, power factor is got 1. Now let's observe something here. Now, if I have power factor to be equal to cos phi, which is simply as R over Z. Now, let's say in the case of where VL is equal to VC, what happened? It now means that what? In this case now, the circuit is at what they call resonance. The circuit is at resonance. We can also liken it to what? ISC. SL equal to what? ISC. I will cancel Y. So XL equal to what? XC. In this case now, the circuit is also at what? Resonance. What is resonance? When resonance occurs in an AC circuit, when the inductive reactance is equal to capacitive reactance, or when the net reactance, when net reactance is equal to what? Is equal to 0. Don't forget, net reactance is what? X net equal to what? XL minus XC. So anytime net reactance is what? Is positive, current is leading. Because during positive now, XL is greater than XC. So net reactance will be what? Will be positive. In that, a current is what? Lagging. Phase angle is lagging. You understand now? Then voltage lead current by pi over 2. Now, anytime XL is less than XC, therefore, net reactance will be what? Negative. In this case, current is leading and phase angle is also leading. And current leads voltage by pi over 2. But when they are now equal, that means another thing has occurred, which is resonance. Now, let's just look what happened there. 2 pi FL, let's call the resonance frequency F0. And let's say that what? Our 1 over 2 pi F0 C is our capacitive reactance. If you cross multiply, I would have 4 pi what? F0, 4 pi square F0 LC equal to 1. Therefore, we are going to have it as what? We are going to have F0. If you make F0 is subject to formula as 1 over what? 2 pi square root of LC. You can confirm that one. That means divide both sides by 4 pi square LC. Then take square root of both sides. If you take square root of what? Square root of 1 over 4 pi square LC. Don't forget, square root of 1 is 1, square root of 4 is 2. Square root of pi square is pi. Then square root will now affect LC. That's how we got that one. So this is the formula for resonance frequency. Resonance frequency. What is the necessity or importance of what? Importance of resonance frequency. When you are tuning your radio, it can be used for better selections. Like, for example, in tuning to a particular station. When you are tuning to a particular station, you perceive something like, you hear something like shh. That shh that you are here that are putting on is resistance. Now, when you get to the station, you get the signal, you get this voice of people who, in that program, you get to hear them clearly. At that point, you have got it to the resonance frequency of that station. So in that case, when we are talking about resonance frequency, is the point where the stations will have a minimum impedance. So minimum impedance occur at resonance, and maximum current occur at resonance. Maximum current occur at resonance. Don't forget that since impedance is equal to square root of R square plus XL minus XC all square. Now it then means that that if this one is 0, according to what we have talked about, we said net reactant, this one is 0. So since it's 0, and we have to put it there, 0 square is 0 plus R square will give us R square. So Z square root of R square, what will it give us? It give us R. So that means at resonance, impedance is equal to resistance. Also, the currents and voltage are in phase at resonance. The current and voltage, no one is leading each other because the inductive reactance is equal to. That means, apart from the case of purely inductive, purely resistive circuit, we now have a special case here where current and voltage are in phase. And that's why the phase angle at resonance is equal to 0. Why? Tan phi is equal to XL minus XC over R. So if this one is 0, that is 0 divided by R will give us 0. And an inverse of 0 will give us 0 degree. Don't forget. So that means the phase angle at resonance is is 0. Another thing again you must understand is that the power factor at resonance is is 0. Is 1, sorry. Why? Because cos 0 degree is equal to 1. Don't forget the phase angle is 0. I told you now. Is 0 degree. The phase angle is 0 degree. So if you put 0 degree here, you understand, man? You are going to have, because 0 is equal to 1 or unity. So the power factor is equal to unity at resonance. Don't forget I told you impedance is equal to resistance. That's why when you plot a graph, a graph of resonance to show resonance frequency, we have what they call the SL, we have the SC. Then we have this point where the two of them meet, the SC meet with SL is what we call the resonance frequency. That point where they meet is what we call the resonance frequency. So they meet at a point here. This meeting point is resonance frequency. So resonance frequency is always with point where the XL is equal to XC, and it produces a maximum current at that point and minimum impedance. Maximum current and minimum impedance for an RLC series circuit. So take note of this resonance frequency. Take note of that. And don't forget the relationship between frequency and inductive reactance, and the relationship between frequency and capacitive reactance. So this will help us to be able to work. Don't also forget that, let me quickly chip this in. There's what we call the quality factor. Quality what? Factor. Quality factor is equal to resonance frequency over bandwidth. Bandwidth. Quality factor is what? Resonance frequency over what? Bandwidth. So if you now want to find, that means that the higher the quality factor, the higher the resonance frequency. Quality factors is what? Ratio of resonance frequency to bandwidth. Bandwidth is talking about the range of frequency of a particular station where you are. So that means that when the range of the frequency of, when this one is high, it will narrow the range of frequency of what? That means when quality factor of that station is high, it will narrow the what? That is the, what do you call it? The bandwidth, the range of frequency of that station, and thereby reducing the unwanted noise. Note that some station that you tune to their station, you begin to hear some noise because the quality factor of that station is not better. Then it will help for better selectivity, a better selectivity. When you are selecting such station, it will enable you to get a better selection of that station because the bandwidth is what? Is that narrow. Don't forget that quality factor is inversely proportional to what? The bandwidth. So the higher the quality factor, the higher the resonance frequency, the lesser the bandwidth, which is the range of frequency, and the better the selectivity of what? Of that station. And it helps to what? To reduce unwanted noise and reject unwanted noise. Don't forget that I told you that when you are tuning to a station, before you get to that station, you will hear some impedance, some resistance. When you get to that station, you get to what? Select the frequency of that station and give you what? A proper signal immediately of that station. So that is just that. Don't forget that quality factor QF is equal to what? 2 pi F naught L over R. That is the formula for quality factor. In case they ask you. Quality factor. Don't forget that the higher the quality factor, it also reduces what? The energy dissipation. It also reduces what? Energy dissipation. And don't forget, the higher the bandwidth, the higher the energy dissipation. So in that case, it's better we use what? We can use that to relate the two of them. Now let's see. In this case now, let us put our what call it? Resonance frequency formula there. I would have 1 over what? 2 pi square root of LC dot L over what? Divide by R. What do we have? This one will cancel this. Now don't forget that this one can also be written as what? 1 over square root of L times square root of C times L can be written as what? 1 times L now. I would have what? L. L can be written in this or logarithm as square root of L times square root of L, then times 1 over R. Don't forget this is R is under and the denominator is equal to Q factor, quality factor. Now, what we're going to have now is what? This one will cancel this. So what do we have as our formula for quality factor? So quality factor can also be equal to what? 1 over R, now square root of L over square root of C, which I'm written as 1 over R square root of L over C. So in case they ask you for what? Quality factor, this is a formula for quality factor. Now, let's go to what? Power loss. Although I might not be able to discuss power loss in this class, I will do a short video on power loss in an AC circuit. So this is what you call it, quality factor in an AC. But basically, the power loss in an AC circuit, maybe probably I will do that one for A level. Power loss in an AC circuit, power loss is called I square R. Power loss is caused by what? Resistor. So, or we can write that I RMS, V RMS cos phi. So this one is what we call the apparent power. So times power factor will give us power loss, power dissipation. So if you study your physics very well, you notice that I just told you that I RMS, V RMS is called, what is this one? I told you power loss is what? R over Z now. remember that V over Z is what? Is Ti. So if I say IRMS times VRMS over Z, I'm not out of place. Don't forget. Times R. If this one is equal to I, it's equal to what you call it? I, which is what? I told you that IRMS is equal to VRMS over Z. Check one of the formula I gave you. So if you put this one now, you are going to have IRMS dot IRMS times R. We are going to have this back. So this and this are the same formula for power loss. But I'm giving other power, for formulas for others of my videos. Go and check before this video. So this is basically the power loss. Then we have what they call what? You can also call it the average power. Average power. Don't forget, in a resistor now, in a purely resistive circuit, this one now, power loss will now be equal to what? IRMS, VRMS. Why? Because cos phi will be equal to 1. And phase angle is equal to 0. Don't forget, in a purely resistive circuit. So basically, I've laid foundation for what we need to know concerning the foundation of what? RLC circuit. We have talked about leading current, lagging current. We have talked about relationship between. Don't forget, they ask what is voltage. The phase angle between voltage across the resistor and voltage across the inductor is 90 degrees. You can be asked. I've seen questions like that. VR and VL is 90 degrees. What about voltage across the capacitor and voltage across the resistor? It's also 90 degrees. I believe I've explained enough. Till we shall see again, same channel. Enjoy your day and have a wonderful time. Thank you for watching and spending your data to watch my classes. Thank you. Expect more by subscribing and put your subscription on notification so that you can always get our videos once immediately we post our videos online. You just on our channels, you just be the first person to see it even before other persons. Thank you for watching. God bless you.